Welcome to this session. I will be showing you how the birthday attacks work. I'm going to take a simple example. I wrote a little Python program to demonstrate the core idea behind birthday paradox in general. So suppose we are sampling, say, elements from a set of numbers, say from 1 to 366, just as an example. The question is, how many items should we have to sample before we get into a conflict? Meaning we wanted to see how many items should we have to select that those two items will have the same value. Okay, so I just took a simple example with 366 possible values, which means those values can be represented using 9 bits. Let me just first run it and then I will walk you through the code. Okay, this is a little Python program. I'm using an online Python compiler for this. What it is showing us is that after selecting 44 samples, it was able to get a conflict. So let's try this one more time and see what happens now when you run it again. Okay, 42. Let's run one more time. 16. Okay. So what is happening now is that the program is actually randomly selecting elements, right, from all possible 9-bit numbers. And it is clear that after just sampling about, say, 16 elements to 20 elements or so, the first conflict has occurred. In contrast to our intuition, at least most of us would think that we would have to sample about 180 atoms before we get a collision. But in contrast, it's instead of half, it's kind of square root. Square root of 360 is approximately about, say, 18 to 20, just to make it easier. So the consequence of this is very interesting from a cryptographic perspective. If we have a hash function, for example, that, say, maps the input to just for fun, only to 32-bit output. Okay, so what will happen in that case? We would think that we can use the same hash function and keep calling it 2 power 32 times before a conflict will occur. But that's not exactly the way the birthday paradox works. In fact, we can get a conflict much earlier than that. So let's see what happens if I just try with 32-bit numbers, right? I have a 32-bit number, whatever number that it was sampling randomly. It turned out that after sampling about 46,192 numbers, which is way less than 2 power 16. 2 power 16 is approximately about 65,000, and 2 power 32 is approximately about 4 billion or so. So we can see that the number of items sampled is significantly smaller than 2 power n, which n standing for n equal to 32. It's actually 2 power n by 2. That's remarkable because the collision will come much sooner than most of us would think. This has nothing to do with Python implementation per se, which I will explain now. What we are using here is the secrets library from Python, and we are asking Python to randomly generate numbers of size 32-bit, create a set of numbers in a set called samples, and we check whether the random number that is just generated is in the sample. If it is there in the samples collection, we will break. Otherwise, we keep adding the random number to the samples that we have. And we measure how many times the loop ran. At the end, we print how many attempts were made before a conflict was detected. So we can try to increase this and see what happens, 40, 50, and so on. But it will be difficult after some point because, say, for example, if you choose 64-bit number, it's going to try an average 2 power 32 attempts before collision is detected. So amazingly, it's only after 800,000 attempts collision was detected. We can actually look for powers of 2. We are interested in that concept in more detail, powers of 2. So we can have a better view of how the numbers grow. This particular website will show us the list of powers of 2. I was trying all possible numbers with 40-bit, right? That's a lot of numbers that we can reach. But the collision came much earlier. It was about 800,000. Let's see whether we can approximate 800,000 close to 2 power. Okay, so it's somewhere between 2 power 19 and 2 power 20. Okay, that's amazing because it's just exactly like half of the power of the size of the number of bits that we mentioned. Okay, so we can say that if we have n bits, then we can have the conflict right after trying just 2 power n by 2 attempts. So that's what's happening in this small case. We tried with 40 and we got a hit after about 2 power 20 attempts. Okay, so this has significant consequence in terms of collision. Collision is the key issue in hash functions, for example, or even collecting random numbers. When you are sampling random numbers, for example, you're generating AES key. What is the probability you will have the same key? AES key usually is 128 or 256 bits long. In that case, you would have to say, let's assume 128-bit key was used. So after sampling about 2 power 64 keys, we will expect the keys to repeat. It doesn't matter how good the random number generator is. That's going to happen because of the birthday paradox. The same with IV as well, the initialization vector. Suppose you are sampling randomly an IV, you would expect IVs to have a collision after you had reached already 2 power n by 2, if n is the size of the IV in terms of bits that you are looking for. Okay, going to show you a Java implementation just to be clear that the observation we are seeing for Python is also applicable for Java as well. Of course, Java is a typed language, so we have more code to declare all the objects and so on, but I will focus more on the core idea. We have a hash set. We will be generating list of numbers, and we keep checking whether the newly generated random number is present in the hash set. If it is present, we get out. That is the idea of this particular Java. Here is the secure random number generator class, which generates uniform random numbers of a given size. And we have a hash set. We keep adding elements to the hash set if the currently generated key is not in the set. And then we check whether did we get a conflict before 2 power n by 2 atoms. So let's give it a try. I'm going to initialize for just 32-bit length to start with. Okay, see what happens, how many atoms it's making before it's getting a hit. Okay, so about 111,000, which is slightly more than 2 power 16. So let's give it a try one more time. Sometimes it will come quicker, but in average, let's try one more time. Yep, here you go. How many atoms it was making? It was only making 29,000 atoms before we got the collision. Okay, so let me generalize what we are seeing so far. We ran the Python code. We saw the same behavior, and the same behavior is also true now for Java. It's simple Java code. We are having a big integer class. We keep computing. We are basically calling the new secure random generator to keep generating new random numbers for us. And then we check whether the set we are having contains the key. If it is there, then we know we faced a conflict. Otherwise, we continue. This is the piece of logic I was just trying to automatically show to you that, okay, after trying 2 power n by 2 atoms, we do have a conflict in general. Okay, so this has significant conflict implications to hash functions. That's the reason why hash functions we expect to have longer output length. If hash functions were just outputting say 32-bit only, then after sampling about 2 power 16 hash function calls, we would be having a conflict. So hash, say for example SHA-1, or SHA-256 for example, the SHA-256 we could expect to have collision after 2 power 128 atoms, which is a huge number. 2 power 128 is beyond what we can do. But there may be other weaknesses in the SHA algorithms in general, but that's not the scope of my presentation or the video demo. It's just to show you how birthday paradox has such a significant implication in cryptography. Okay, thank you very much for your time. That's all.